Hi, in this video, I'm going to demonstrate to you on how to conduct the crank and slotted lever quick return motion to collect the data for this experiment. So this is the crank and slotted lever quick return motion apparatus that we're going to use for this experiment. Let us first look at the main parts of this apparatus. So it consists of a crank, and this crank is of a fixed 40 mm length from the point of rotation, which is O, to the end of the crank. Then we have this lever with a slot and it's linked to the crank. So this lever length is also fixed. So from this point to the another end point of this lever, it is 240 millimeter. And you can see a slider here. So this is a slider. So this slider would actually move forward and backward during the cutting operation of the machine. And then of course, when this mechanism is in use in a cutting machine, example, in the electrical power saw, so this crank is actually connected to a motor. So motor will rotate and provide the rotational motion required. And through a mechanism like this, so this rotational motion of the motor, so it can be converted to a translation motion of the slider. So when this is in use in a cutting machine, we have the sawing blade which is fixed on the slider. So to cut the workpiece, so we have to clamp the workpiece on the vise, and we bring down the saw blade to touch the workpiece, and we start the motor. So motor will rotate. So this rotational motion through a crank and slotted lever mechanism, it will be converted to a translational motion so that we can cut the workpiece. Not only this mechanism transfer rotational motion or convert rotational motion to translational motion, so it also provides a faster returning for the returning stroke compared to the cutting stroke. So the cutting stroke is slower because during the cutting stroke, the cutting tool will actually cut the workpiece, and then during the returning stroke, the cutting tool is not doing any work, it's returning to its initial cutting position. So we need to have a quick, faster returning in order to save time, and this can increase the efficiency of the casting process. Well, before we start with the experiment, so make sure that the apparatus is working fine. So try to rotate the crank and make sure it can actually function well. It can be rotated freely. Well, so this apparatus is working fine, so it can be rotated freely without any problem. So to start with the experiment, you can see there are two scales here. So this is the horizontal scale for us to record the position, or we call it the displacement of the slider. And another scale here, so this is a circular scale, and it's labeled in angle degree. So this is for us to read the angle of the crank when we increase the crank angle every time with a 10-degree increment. Well, to start with the experiment, so make sure this crank is at 0 degree angle. It's at this position. So at this position, crank angle is 0 degree. So jot down the position of the slider. So if I read it from here, I get 70 mm, which is the initial position of the slider. So I increase 10 degree of the crank, and then I jot down what is the reading using this horizontal scale to get us the displacement of the slider. Increase another 10 degree, and I jot down the reading of the slider again. So do this for a full complete revolution of the crank. So until the crank angle actually return it back, it returns back to a 0 degree angle. So as you rotate this crank here, so you can see there will be two motion of the slider. One is forward and one is backward, or one is down, one is up, for a complete revolution of 360 degree for the crank. So you can see there are two limits of the slider. So one limit is at this end, and another limit is at this end. And then you, from the corrected data, so you can actually determine the amount of angle occupied by each of these two strokes. So one of these strokes is actually the cutting stroke, which is at slower speed, and the other one is the returning stroke, which is at a higher or faster speed.